Hey guys, it's Taylor. Welcome back to Taylor Tech. Don't you just love it when you shoot like a 20-minute video and you get to the end of it and you realize the camera wasn't recording? It's great. Anyway, today we're going to be doing a little audio 101. So as we go through and talk about gear and equipment, it's really important to have a basic understanding of some of the core concepts of audio so that as you look at spec sheets and things like that, you understand the implication of numbers immediately. So we're going to go through 7 or 8 core concepts that are going to arm you with the knowledge that you need to understand what you're looking at as you're looking at different audio gear. All right, guys, the first and most basic thing we're going to talk about is sound. Now, sound is a mechanical pressure wave through the air or water or metal, anything else, that creates the actual noise that we hear. Its intensity or volume is measured in pressure variation, which is pascals, the SI unit for pressure. And its frequency, or the pitch and tone of it, is measured in hertz, which is the standard measure for frequency. The reference values are 1 Pascal variation from top to bottom of the sound wave is equal to 94 decibels of sound, and 1 hertz is a 1 second wave. Now, 1 hertz, very, very low. That's far below the range of human hearing, but that is the reference value. The second thing we're going to talk about is signal. Now, signal is an electrical or digital representation of a sound wave. So the electrical representation being the analog version and digital, of course, being digital. It's measured in millivolts with a reference value of 1 volt equals 0 decibels of sound. So because this is the reference value, signal is often displayed as a negative number of decibels. So I'm not really going to go into the difference between analog and digital sound today because there's way too much information to cover there, and that's far beyond the scope of what I'm really trying to get at, although it's very important information to have. What I'm going to do is I'm going to link you to the xfi.org, xiph.org website where they have some videos that go into great detail explaining this. Now, it is about an hour total watch time to watch both videos that they have there, but it's very much worth it, highly recommended. These guys are brilliant, and they're the guys who wrote the FLAC codec, if that tells you anything, and they really understand what they're talking about. So if you want to really understand digital audio, go watch those videos and come back and finish this one. All right, so now we talked about sound and we talked about signal, and in both cases we talked about decibels. Now, that may seem a little bit confusing, especially since the decibels don't really seem to be in the same range most of the time, especially considering signal is usually displayed as a negative decibel value, which is impossible. You can't have negative sound pressure. That doesn't really work that way, especially because it's measured as a variance. So the important thing here is that not all decibels are the same, right? Sound is still measured in pressure variance. Signal is still measured in voltage. It's just that the decibels are actually just a logarithmic scale that's used on both. So sound decibels are usually displayed as dB SPL for sound pressure level, and signal decibels are usually displayed as dBV for decibels of voltage. So it's really important when you're reading a spec sheet that you understand what kind of decibels you're looking at, because it's going to make a big difference on what they're trying to tell you. And lastly, when it comes to that logarithmic scale, it's really important to understand that not all decibels are created equal. So as you move along the scale, it increases exponentially. That's what a logarithmic scale is. So as you go from 10 decibels to 11 decibels, that's a much smaller jump than to go from 100 decibels to 101 decibels. So yeah, just keep that in mind as you're looking at those numbers. A very small difference in the number of decibels can be a very large difference in how effective something actually is. All right, next we're going to talk about noise. Now, noise is the sound or the signal that we aren't wanting to hear. And this is more of like a term of art because technically all sound is noise of a type. But when it comes to audio, when you're talking about audio, noise is what you don't want to hear. So really we can divide noise into 2 things, background noise and line noise. And that's how I usually refer to them, although those are not necessarily the technical terms for it. Anyway, background noise. Background noise is the actual sound that is occurring that I didn't want to hear in my final result. So That can be the air conditioner running, it can be the toilet flushing, someone opening the garage door, someone talking off camera. All of these things are background noise. Next, line noise. So line noise is that electronic hum that you'll sometimes hear, if someone's, got a crappy mic, or if, sometimes you'll hear like your GPU kick on while you're talking on your mic, and it makes that really annoying hum. That is line noise, and it's basically electronic interference with an analog sound signal. All right, next we're going to talk about sensitivity. Now, sensitivity is the way that we measure how well something converts from sound to signal, or vice versa, from signal to sound. In the case of converting from sound to signal, we're talking about microphones. Now, this is measured in dBV. So we're looking at the output of the microphone. It uses a reference input of 94 decibels of sound at 1 meter. So then this is how much signal is the microphone producing. A higher number is better. A more sensitive microphone that captures a sound better allows us to use less gain when we're capturing the sound. This means that we can keep down the line noise in our devices because we're using less gain. When it comes to speakers, sensitivity is just expressed in decibels SPL. So we're looking again at the output. How much sound pressure are the speakers generating for a given input. That input is 1 watt of power at 1 meter away from the microphone that's testing it. So again, a higher number is better. A speaker that can produce more sound for less input is going to allow us to use less gain as we're in the preamp phase, less level in the preamp phase, and less wattage in the post-amp phase. Both of which will allow for more room to create sound in. Next, we're going to talk about signal-to-noise ratio, or SNR. And this is a very common metric that you're going to see on almost every device out there, be it a microphone, a mixer, an amplifier, a signal processor. And what it's telling you is the ratio of signal to line noise that you're going to get on a device. So it's, so as a ratio, if it's got a signal-to-noise ratio of 80, that means 80 decibels of signal to 1 decibel of line noise. So this is a very important metric because line noise can be additive as you go through devices. If a microphone generates a certain amount of line noise, it's going to be amplified in the preamp phase. In the mixer, it's going to be amplified by the amplifier, and you get a lot of noise at the end of the day. So it's really important to pay attention to signal-to-noise ratio, and a greater signal-to-noise ratio is always better. All right, so the next three kind of go together. So they are noise floor, headroom, and dynamic range. And essentially what these are telling you, the noise floor is telling you how low of a signal you can process with a device before all you get is noise. Because the lower a signal is, the more likely you are to have interference. The headroom is telling you the maximum signal that you can put through a device before it clips, which it means that it has gone beyond what the device is capable of accurately reproducing, and you end up cutting off the sound. And those two together create dynamic range, which is the difference between noise floor and headroom, and it's of course expressed in decibels voltage. And this tells you how wide of a range of sound a device is capable of reproducing, from the lowest, quietest sound to the highest, loudest sound. So you always want a wider dynamic range. You want a higher headroom and a lower noise floor. That lets you just create create more dynamic sounds. Again, dynamic range, lowest to highest. All right, guys, I hope this video has been helpful for you in terms of explaining some of the core concepts of audio so that you have a little more knowledge as you look at the spec sheets for gear out there. There's links below to all the places you can find me on the internet, Twitter, Steam, Reddit, and I really appreciate you watching. Thanks, and have a great one.